Hello, everyone. My name is Dmitry. I'm CTO of Fluent. Today, we're going to talk about EVM, SVM, WebAssembly, and why it's so extensible, and what is blended execution in these terms, and how it's all connected together. So, the first thing, blended execution is the state transition representation primitive that is used inside Fluent to unify virtual machine and execution environment. What does it mean? And why it's so extensible? So let's figure out. The first thing before we start, let's start with introduction of Ethereum architecture. Oops. And how Ethereum works. So in normal Ethereum world, you know that there is Ethereum that uses different components inside, like RPC API, like peer-to-peer for networking, and additionally, for example, storage layout, storage. And also it has EVM, the most interesting part of Ethereum. What's the difference between, let's say, Ethereum architecture and Fluent architecture? So it's almost the same. Let's say there is Fluent, and Fluent has all the same components like RPC, peer-to-peer, storage, and etc. I don't know why I write storage like this, but what to do? But instead of EVM, Fluent uses different virtual machine. Fluent uses Wasm. So Fluent replaces virtual machine with from the default EVM with our customized Wasm virtual machine. This is the major difference. But still, the question is, where is blended execution and how it appeared? So before we start, let me explain what is virtual machine, what is execution environment, and what is EVM. Virtual machine, execution environment, and EVM. So virtual machine is this one. Virtual machine. Virtual machine is a limited specified stateless instruction set executor. So it is, let's call it a library or program that understand some limited instruction set and execute this instruction set. In the sentence before, I mentioned that it's stateless. It's quite important because from our perspective, virtual machine doesn't explain how to operate with an external state. For example, how to access storage, how to access context information like block context, transaction context, or your execution context, including balances, assets, and etc. But execution environment is different. Execution environment wraps virtual machine and adds additional standards that is used to specify how to access, how your application can access account information, balance information, transaction information, block information, etc. So by knowing these two terms, let's define what is EVM. So EVM stands for Ethereum Virtual Machine, but we don't think it's virtual machine. EVM is a stateful instruction set executor. So as you remember, we defined VM as stateless. Why we call here EVM as stateful execution, stateful instruction set executor? Yeah, right. Why it's stateful? Because EVM has a lot of instructions. Let's say instruction balance. You cannot execute this instruction if you don't know anything about your execution environment. So EVM is strictly dependent on its execution environment, and it cannot exist without execution environment. So we want to say that EVM is something like EVM is VM plus execution environment. Of course, you can extract a subset of EVM instructions and say that now it's stateless, but in most of the cases, it can be useless. You can also say that EVM defines standards for interaction, but it also limits developers in the way how they access information, how they manage call data, how they manage context information, and they're actually quite limited with the context. So we wanted to bring EVM into Fluent. But how to do this? Instead of integrating it directly into Fluent code base, we just created a smart contract. We call this smart contract EVM loader. Actually, we have two smart contracts, loader and deployer. So EVM loader and EVM deployer are WebAssembly-based smart contracts that are written on Rust language. Rust. These contracts are written using Rust language, and they execute EVM transition, but not only EVM transition, because it also includes execution of, for example, different EEP standards, like information about how to charge gas, how to charge, how to execute access lists, how to access storage, how to access account system, etc. So it includes all this information inside these special loaders. And we figured out that if you can specify the loader for EVM, and you can encapsulate all EEP standards inside this application, inside this small application, then you can do the same for all remaining execution environments and virtual machines. For example, you can take execution environment or virtual machine that, let's say Solana, and we can create a set of loaders and deployers that follows SVM deployment and execution scheme, or almost will follow this scheme, and we can execute applications that are created for these applications. And why it's so extendable? Because before we go to extensibility, I want to mention that one of the most important parts here that for sorry, for EVM, we specify a so-called transition function. So transition function is a function that consumes some input and produces some output. So transition function transits state for EVM. And for SVM, we need to figure out how to define function that do the same state transition. Also, we must keep in mind that, for example, SVM uses different storage layout, it uses different account structure, it uses different even cryptography. So we cannot easily embed SVM inside. So I will explain the solution. The solution is quite simple how to do this. So before I give my explanation, I want to introduce the following. I want to say what is blockchain. So everyone knows that blockchain is a chain of blocks. All these blocks are connected using block hash, and we're using previous block hash. So every block stores information about previous block and etc. And each block contains information about modified state. So about the state it modified during execution. And when you transit a state from block A to block B, we call it state transition, because you take two blocks, let's say block A and block B, and you can verify a state transition. So to verify state transition, you need to have a state transition function. So a function that defines correctness of this transition. The same I explained here for EVM, for SVM, as you remember. Actually, this rule works for everything. Let's say we have an instruction that add two numbers. Uh, let's say A plus B. So we can create a transition function that takes these two numbers and verifies that it matches the exact results. Yeah. So once you transit the state from block A to block B, you need to prove correctness of your balances modification, of your accounts modifications, and etc. And as you know, inside the state, you have all information related to your balances, accounts, storages, bytecodes, etc. State is a tree. State. Wait. State. Where is my? Here it is. State is a tree. Tree like this. It's also tree. It has branches. It has root. Here is root. It has leaves. And inside leaves, we store some useful information. It can be accounts. It can be storages. Storage. How to write storage? I forgot. It's really strange. And inside block transition, inside block transition function, you verifies correctness of transition of your state from A to B. So inside blocks, you have information about root A and root B, and you prove correctness of the transition. So now we understand that to verify the transition from state A to state B, you just need to create a function. So Fluent or blended execution helps developers to define such functions. So if you want to prove the transition, you just need to create a function that matches your specific execution environment needs, including your standards, including your virtual machine, and etc. But it's not as simple as you can think because of several problems. Let's say you have a state tree. Here's a state tree, and you want to store information about accounts inside your leaves. So you have so-called a binary path inside the tree. So if your account exists here, uh, then your path is 0, 1, because here you go left, here you go right. Actually, here I show the simplest binary tree, but for example, Merdel Patricia tree works is almost the same manner. There's not much difference, just for simplicity. So, you can specify the path inside your tree and how you achieve the path. And the path is calculated using your address. So you have your address. It's called address. Address. What is address? In Ethereum, you take your private key, you calculate your public key. So your public key is G times X, where X is your private key, is your secret key, and G is your public key. Then you uncompress it and calculate key check of your public key, of your uncompressed version of public key, and cut 12 bytes. And this is how you get your address. And using the address, you can calculate a binary path inside your state tree. So if we know this, can we theoretically store different accounts in the same tree? I mean, accounts that uses different cryptography. Yes, we can, because Solana uses different cryptography. They uses G times SHA-512 of X, and here we use SEC 256 K1 curve. Here we use Edwards curve. ED25519 curve. So it uses different curves. Since it uses different curves, it means it cannot intersect anyhow inside your state tree. And you will get different paths inside the tree. But what if you want to send assets? For example, we have a very solid EVM user and Solana enjoyer. And we want to send some tokens to this guy. How to do this if cryptography is different and we don't know the path in the tree? So actually, we can calculate the path because we know address of this guy, and we can ask his address, and we can convert it to Ethereum address that matches exactly the same binary structure. So, and when we send our assets, we send to this special magic address, and our SVM user receives these assets in his wallet, and he can see here, or she can see his new assets in his wallet. And opposite operation is also possible. If SVM user want to send his coins back, he calculates the recipient special magic address and send all these funds, for example, using his default Solana wallet. And they share the same state tree. So we have just figured out how balance transfer works, how accounts work, but how it works for smart contracts. Because smart contracts also uses different language. Because, we have EVM, we have SVM. So EVM uses solidity and the EVM instruction set. SVM uses trust and special so pact plus RP. Where is P? RPBF binary representation. EVM uses EVM, just EVM. Of course, it's also wrapped into different transaction types. It's also wrapped using different cryptography, but it's not important right now. So if you create application using EVM, we already know that we can create EVM loader that executes EVM binary. So it's literally EVM interpreter. There are several ways how you can optimize this. For example, we can create a ahead of time compiler that translates EVM into WebAssembly. In this case, there is no need to have an additional interpretation stage, and we can literally execute everything natively on file using a ahead of time compiler. So for SVM, since it already uses RPBF and its binary structure, we need to do almost the same. We need to define SVM loader. Oops. SVM. So SVM loader can be used to define rules how to execute SVM applications. And this is the most tricky thing, honestly. Why it's so tricky and why it's so important? Because in SVM, there are several limitations and constraints. Let's say the most important limitation is how they manage accounts, how they manage storages, also how they manage how you call this? Different constraints like transaction size, because transaction size, as remember, is limited with is 1.2 kilobytes in Solana, and you cannot. And if you want to deploy an application that exceeds the limit, then you need to create special buffered account, accumulate your bytes into these special chunks. into special buffer and then converted from to executable format. And it's quite inefficient for us to support this model, because if we implement pure SVM, then we need to create our buffered accounts, we need to create loaders for this, we need to create converters that translates it from a buffered account into execution account. For us, there is no need to put such constraints because we don't have 1.2 kilobyte constraint as Solana has. So we're not limited with this. So instead, we can modify SVM loader a bit. So let's say we don't want to limit developers with 1.2 kilobytes. So deploy any application you want. As you know, this limitation exists because of MTU size. That is Ethernet limitation, and it is used just to optimize who's sending packets over internet. And instead, we can create a loader that consumes the full buffer that contains all bytecode that is required for the deployment process. But if we modify deployer, and if we create new SVM deployer, then we need to change a tool set of Solana. So if we change tool set of Solana and we create our own SVM deployer for users, for developers, it's 100% compatible with original Solana features, and in this case, developer experience of developers is not affected at all. But if we create another deployer, then we have a question: why do we need to have to support SO files with RPBF standards inside? So this is a good question. We're researching this question, and our take right now that there is no need to support RPBF at all, because instead you can just recompile your SVM application into WebAssembly. And since Fluent runs customized deployer, you can use our custom deployer to deploy your existing SVM applications. And the only thing you need to do is just to recompile it to WebAssembly. So you just need to specify a different target, a different compilation target, because originally you used RPBF target, but now you can use WebAssembly target. For most of the developers, it's only one line code difference and nothing else to do. And this is how they can get this by default. So I highlighted how EVM works, how SVM works. The thing I didn't mention before is WebAssembly, because WebAssembly is a foundation of the execution. And Fluent blends WebAssembly in the same manner as EVM and SVM. So developers can upload the native WebAssembly binaries, the bundles, and I call it bundle because it contains all information about, for example, how you manage your memory. So there is no need to wrap it into ELF, into SO. It has, it's quite self-explained. It contains a lot of different sections like memory, data, also global data, and etc. This is why I call it bundle. And you can create an application using WebAssembly. So to do this, we provide special. Let me be a bit more careful. WebAssembly loader. And actually, we also provide special WebAssembly deployer. If you didn't get what are all these applications, EVM loader, SVM deployer, Wasm loader, Wasm deployer, all these things are smart contracts that we develop and deploy on Fluent. So it means if EVM loader, SVM loader, and etc. are smart contracts, then you can upgrade these contracts. So it means that if, for example, there is a new heap for EVM, we can do a forkless upgrade for EVM loader or EVM deployer and support new recent Ethereum standards. There's no need to do a hard fork for this. So we literally do an upgrade, and this is how Fluent can achieve forkless upgrades. But what I wanted to say, I want to say something very, very important regarding upgrades. Okay, I forgot what I wanted to say, but it was really important. Yes, so, and using this model, you can do forkless upgrade, for example, for EVM, for SVM, for WebAssembly. And it doesn't even limit Fluent because if we can do forkless upgrades, if we can define different execution environments, and since we know that all these execution environments are smart contracts, then we can theoretically create a fully trustless execution environment. By trustless, I mean when developers can create their own deployers and their own loaders and enable it as smart contracts on the chain. So if, for example, if developers want to extend Fluent's functionality and bring more virtual machines, bring more execution environments, they can do this using, for example, special SDK that Fluent can provide for this. In this case, they also define the deployer and loader. And both these contracts are used to prove transition of this custom execution environment. For example, right now, Fluent blends EVM, SVM, and WebAssembly. WebAssembly is used to help developers to build on the edge between different execution environments because it's unified, and developers can, for example, create some symbiotics between EVM, SVM, and combine different contracts, different ways to interact between them, and etc. Actually, there are a lot of things I wanted to highlight and explain, but I think it's better to do it as a second round of our whiteboard session the next week, where I can explain how all these things are connected to ZK and why ZK really matters here. Because also I didn't explain what is our Wasm and why do we need our Wasm and how it affects our ZK proving model and how our ZK proving model actually works. So if I think that's it for the current topic. If you have any specific questions regarding blend execution, extendability, then ask in the chat. So we have a question. Does it support ZK functionalities? Actually, I didn't want to answer on this question originally because I want to highlight and explain how it affects ZK, but I can do a very brief explanation. So here, we introduced a transition function. So, and now we know that we can wrap, for example, everything inside transition function. We can wrap EVM, we can wrap virtual machine, we can wrap execution environments. So our EVM loaders, SVM loaders, WebAssembly deployers, and etc. All these things are just transition function. And we create a transition function, a state transition function that transits states from A to B. So, and it calculates a state transition. And we create a function that transits the state. Since we have function, we can compile this function into WebAssembly. Actually, we compile it to Wasm. Wasm stands for Reduced WebAssembly. It's an optimized version of WebAssembly. I can explain what is optimized in the next whiteboard session. And then we unroll RWASM into ZK execution trace and use it to prove correctness of all executions. So, and then of course we roll up all these computations into Ethereum. How does Fluent handle VM-specific features like Solana parallel execution or Ethereum's EVM precompile in a blended environment? So we have two questions here. The first one is precompiles. The second one is parallel execution. So regarding precompiles, everything is quite simple because since we have WebAssembly and we use WebAssembly as a first citizen language, then we can just compile all Ethereum precompiles and deploy them as smart contracts and embed them inside Genesis state. So inside Genesis, we have all functions, for example, identity function, for example, SHA-256, for example, RIP-MD 160, and etc. Also Blake 2. All these functions we support as we compile to WebAssembly and we embed inside our execution environment, inside our Genesis state. Of course, we optimize it in terms of proving. And for example, for SHA-256, we create special magic bindings that we replace with special circuits that are more efficient to prove. The same we do with Kichak, with Poseidon hashing, and etc. But the basic concept is that we represent everything as a smart contract. There is one minus in this concept. The minus is that it can affect gas measurement a bit. So in terms of EVM standards, we're going to be like, so-called type, as I remember, 2.5. So EVM compatible, but with different gas policies. Regarding parallel execution, so Ethereum can execute transactions in parallel. That's true, because Ethereum uses access lists. Wait, give me a second. How to write access lists? And we use strict access lists. Strict access lists. Since we have strict access lists, then we can extract information about all addresses affected, about all storage slots affected. And we can do the same for SVM. For SVM, we can, this works for EVM. For SVM, we extract accounts lists. And then using this information, we can merge and use it to parallel execution for Ethereum and for SVM. In this model, there is a limitation. A limitation happens because you need to be sure that all execution environments you integrate, they have similar, let's call it behavior. For example, if you want to bring parallel execution, then you can bring it for only the part of transactions that supports parallel execution. Because most of these balances, they store in different state paths, and they cannot directly intersect. They can only intersect using special, like some sort of helpers or adapters, etc. And you can theoretically execute Solana transactions independently and use special bridge. I don't want to call it bridge, let's call it message hub, to interact and do on-chain native interaction between EVM and SVM, for example. This is the concept. So theoretically, we cannot support a native Solana parallel execution, but we create new parallel execution. And we can also parallel Solana transactions with EVM transactions. Also, we're having the third question. What's the approach for keeping different VM implementations up to date with their respective mainnet versions? So, yeah, I explained it before, but I can repeat. So, since all our deployers and contracts, deployers and loaders are smart contracts, and we use WebAssembly to define these contracts. Since they are contracts, we can do forkless upgrades of the execution environments. And once a new version appears with new, for example, EVE standards, why not? And we want to enable these new EVE standards, then we can just initiate an upgrade process and migrate our deployers and loaders to support new Ethereum standards. The same happens, for example, with Solana loaders and with all other execution environments. Theoretically, we can integrate in the future. Okay, so is there any questions except the three we have just highlighted? Okay, it seems there are no questions. So thank you all for joining today's whiteboard session, and we're waiting you for the next session where we're going to highlight and cover ZK, our Wasm, and virtual machine problems, and how Fluent instruction set works, and how it's all connected to ZK. Thank you.